Professor Carlos Frank of Durham University reflects on his life's work, saying that while his theory of the universe is now being challenged, he sees this as an opportunity for growth and scientific advancement. The James Webb Space Telescope is revolutionizing cosmology, challenging ideas that have been accepted for over a century. Its latest ultra-deep image has exposed errors in astronomical understanding. Instead of simply revealing the universe's first stars, the telescope is dismantling previous assumptions and paving the way for a new era in science. While some researchers are apprehensive about these revelations, many embrace them, recognizing that flaws in existing theories have been evident for some time. For instance, inconsistencies in measuring the universe's expansion rate should have raised alarms long ago. Yet, the scientific community often clung to outdated concepts rather than confronting these anomalies. One cornerstone of cosmology, the cosmic microwave background radiation, is thought to be the universe's oldest light, emerging approximately 380,000 years after the Big Bang. This period, known as reionization, marks when the universe cooled enough for electrons and protons to combine into stable hydrogen atoms, allowing light to travel freely. The CMB was accidentally discovered in 1964 by American physicists Arno Penzias and Robert Wilson, who detected a pervasive noise while testing new antenna technology. Their finding, later confirmed as evidence of the Big Bang, earned them a Nobel Prize and solidified their legacy in astrophysics. The CMB offers a glimpse into the infant universe with its minute temperature variations providing critical insights into its early conditions. Today, scientists continue to rely on the CMB as a foundational tool for understanding the universe's fundamental metrics, such as its expansion rate. This work builds on calculations first undertaken by astronomer Edwin Hubble in the late 1920s. Edwin Hubble discovered that galaxies are moving away from us in all directions, with their speed increasing proportionally to their distance. This observation became known as the Hubble law, or the Hubble constant. However, Hubble's measurements lacked the precision achieved by later techniques. When the cosmic microwave background was identified, researchers recalculated the universe's expansion rate and found it significantly lower than Hubble's original value. Subsequent recalculations used Type 1, a supernovae, as standard candles, astronomical objects with consistent brightness that allowed for more precise distance measurements. By comparing a supernova's observed brightness to its intrinsic luminosity, astronomers could calculate distances with remarkable accuracy. The expansion rate derived from the CMB is approximately 67 kilometers per second per megaparsec, while measurements based on supernovae yield about 74 kilometers per second per megaparsec. This mismatch, known as the S8 tension or Hubble tension, has been a persistent challenge in cosmology since the 1990s. It points to potential flaws in either measurement methods or the very concept of universal expansion as we understand it. The implications of this tension go beyond mere discrepancies. They suggest that fundamental aspects of our understanding of the cosmos may be incorrect. For years, researchers struggled to explain these differences. However, the advent of the James Webb Space Telescope has brought unexpected revelations that could help resolve this puzzle. The JWST has uncovered ancient, mature galaxies that seemingly formed before the Big Bang, a discovery that challenges the foundational principles of cosmology. This is no longer seen as a minor inconsistency. It represents a profound crisis in modern astronomy, forcing a reevaluation of long-standing scientific paradigms. The current crisis in cosmology raises not only doubts about the universe's expansion rate, but also questions the very foundations of the Big Bang theory. Webb's images reveal a cosmos that appears fundamentally different from long-held assumptions. The S8 tension served as an early warning, but those clinging to traditional theories now face profound challenges. Do we truly understand the universe? For many researchers, decades of work now seem uncertain as they grapple with the unexpected discoveries. This crisis forces us to confront a critical question: how much do we really know about the cosmos? To answer, we must consider how science operates. Theoretical science relies on a web of mathematical models, empirical observations, and deductive reasoning to infer general principles and specific predictions. However, theories are not immutable truths, but rather constructs based on observed phenomena, experiments, and analysis. Our practical knowledge is limited to data collected from telescopes, radio waves, and advanced detection systems such as neutrino and gravitational wave instruments. The James Webb Space Telescope offers an unprecedented ability to analyze the universe's oldest light, breaking it into individual frequencies to determine the composition, mass, and structure of galaxies over 13 billion years ago. Webb can also identify the motion and shapes of these galaxies. However, it has its limitations. Some observations may confuse galaxies with black holes, which emit similarly bright light from their accretion disks. Science has long favored certain assumptions, often dismissing alternative explanations. The discoveries from Webb challenge these established ideas, urging us to replace outdated theories with new understandings, as has occurred throughout scientific history. Yet, the current findings are so extraordinary that scientists are cautious, hesitant to propose new frameworks amid such foundational uncertainty. Modern physics remains deeply rooted in the teachings of Isaac Newton from the 17th century. His laws of motion and gravity provided a solid foundation for understanding physical phenomena on Earth and beyond. However, these ideas required expansion in the 20th century when Albert Einstein introduced the theory of relativity. In 1905, Einstein's special relativity revolutionized our understanding of space and time, showing their interdependence on the observer's motion. By 1915, his general relativity provided a groundbreaking explanation of gravity as the curvature of space-time by massive objects like stars and galaxies. While Einstein's theories addressed many questions, he acknowledged their limitations in describing the universe as a whole. His dream of a world formula remained unfulfilled, a challenge that persists today. As physicist Michio Kaku has suggested, solving this mystery would likely secure a Nobel Prize. Where might the errors lie? Have phenomena been misinterpreted, or are technological limitations to blame? Central to the crisis are the elusive concepts of dark matter and dark energy. Together, they are thought to comprise 95% of the universe, yet their nature remains poorly understood. These enigmatic components may hold the key to resolving the cosmological crisis. However, dark matter and dark energy, which dominate current cosmological models, remain elusive. Neither has been directly observed, and their existence has never been definitively proven. This leaves us with two possibilities. Either they do not exist, requiring entirely new explanations for the universe's expansion and galaxy dynamics, or they possess unknown properties that challenge our current understanding. A radical hypothesis proposes that the properties of these dark components have evolved over time, with some even speculating that they could exhibit a form of intelligence. Another concept under scrutiny is gravity itself. As a force that supposedly arises from mass or the curvature of space-time, its nature has been supported by Einstein's theories and confirmed through various observations. Yet, we cannot entirely discount the possibility that gravity behaves in ways we do not yet understand, or that an entirely different mechanism is responsible for the observed attraction between objects. Cosmology relies on certain values known as cosmic constants, which have been considered stable and unchanging. However, small deviations in these constants could significantly alter our understanding of the universe. Some calculations suggest that the dynamics of the cosmos could be explained without invoking dark energy, hinting at alternative explanations for observed phenomena. Redshift, a key indicator used to measure cosmic distances and the age of galaxies, could also be misunderstood. If this fundamental metric is flawed, decades of assumptions about the size, scale, and age of the universe would need revision. Similarly, our interpretations of the cosmic microwave background radiation, long considered a remnant of the Big Bang, could be incorrect, raising doubts about the universe's origins. It's even conceivable that the universe did not emerge from a single starting point, which would challenge the very idea of the Big Bang. Even with our advanced technology, the possibility of errors in instruments like the James Webb telescope or in data processing and interpretation cannot be dismissed. Engineers and scientists acknowledge that mistakes, however minor, can occur and could contribute to the current scientific crisis. These unresolved mysteries remind us of the complexities of the universe and the limitations of our knowledge. In light of these challenges, cosmology stands at a crossroads, poised for potential breakthroughs that could reshape our understanding of reality.